Welcome everybody to your favorite podcast on the interwebs. I'm Hari and my partner is Jeffrey, and today we'll be talking about the ins and outs of Unit 2 of Statistics. Let's first start by how the CED orders it. So, how are variables related, you might say? Well, I got you with that answer. There are two different bivariate data slash variables. There's a categorical version, which can be represented by histogram, which you will now see on your screen. And that is how a histogram looks. Now we'll be looking at the quantitative version, which is another type of bivariate data. And that is represented by scatter plot, which will now be represented on your screen right there. So that's basically how variables are related. You can just plot them into a plot and you got them. Now let's talk about how do you represent two categorical variables. That might be tricky, you might say. Don't worry, we got you for this one too. So there are many tables and diagrams you can use. A table is like a two-way table, which you see on your screen right now, where it has two different sections or cutouts. There is a variable called joint relative frequency. This isn't a table necessarily, but instead this is just new information you need to learn for Unit 2. And it's basically the ratio of the frequency in a certain category to the total amount. So, for example, on the image you see right now, the joint relative frequency of people who like snowmobiles but don't like skateboards will be 25 out of 105, because there's 105 total of people who like snowmobiles. Now we will be talking about a side-by-side bar graph, which will now be represented on your screen. You see right here that instead of just having one bar for each section on the x-axis, it's actually having two bars where you can compare, as like in this graph, it's comparing females to males. There is also a graph called the segmented bar graph, which you shall see on your screen now. You see it right here. It looks very funky when you first have a first glance on it, but once you see, they have like a table to the right of the graph, or an index as some people call it, and that is basically a color-coded version of what this graph represents. And yeah, so now we will be talking about statistics for the two categorical variables. So the next image you see will be a two-way table, but this will help you understand what marginal frequency is, which will be the next topic that we're talking about. And you see right here, marginal frequency is the relative frequency of all the people in a certain category. So as you see right here, all males, the marginal frequency is 60 because there's 60 total males. Or like down here, sports utility vehicles, there's 156 total sports utility vehicles, and that's the marginal frequency. Next, you'll see a same two-way table like this, but instead it will be showing a frequency called conditional relative frequency. This frequency you basically use this frequency if you know the marginal frequency, and as you can see here, I think you guys can guess this, but it's basically dividing the amount of that specific category by the total marginal frequency. So like we said, there were 60 males, but there's 21 males who also had a sports utility vehicle, so it's 21 divided by 60, and it gives it in decimal form. And as you can see on total side, there is just a straight 1. Okay, now let's stop talking about categorical variables. I know y'all are tired of this, for sure. So now we'll be talking about how to represent the relationship between two quantitative variables. So usually when you want to represent the relationship between two of them, you usually use a scatter plot. And I'm pretty sure you guys know what a scatter plot is. So I don't believe we will. Actually, we do have an image because we have a killer video person. As you can see, a scatter plot is basically a bunch of dots on a plot, which helps tell you many things like the frequency and things like that. So when using scatter plots and like analyzing them, we use the acronym DOFS. What is DOFS, you might say? Well, I got y'all. DOFS is direction, outliers, form, shape. So it's similar to how you guys may have learned to write in Frappy in your school as SOX, which is shape, outlier, something something. Uh, and when you see here, to find a direction, if it's positive, negative, you find the slope of it. And if the slope is positive, so is the direction. And if the slope is negative, that is also the direction. However, if you can't tell what the slope is, then that means we just don't know what the direction is, and it's just unclear. Outliers. Basically, there's no real way to help explain how to find outliers. You just look on how far away something is from the total scatter plot, which you can kind of see at the very top on the 80 axis. There's two dots just like sitting by themselves enjoying their time, and we can assume those two are outliers. So, form. That is whether or not a scatter plot is linear or nonlinear, which also means if it's linear or curved. So as you can see right here, we would assume that this is linear because it does not look like a curve and it looks more like a linear line. Now, shape slash strength. To become more clear on how to understand this, you need to know what this R variable is called, and this you will learn in 2.5. So essentially what you want to know is how strong is the correlation, and is a linear line very clear to point it out, or is it more scattered around, meaning is it weaker? So when you're writing about this, you want to use words that end with ly, like moderately, fairly, and clearly. And with the words and the strong and weak to specify the stuff, that will basically be how you write for the strength. Now we'll be talking about correlation.
I'm going to be explaining correlation, so which is 2.5 in the AP in the College Board CED. So what is correlation? Correlation is the measure of direction and strength of a relationship between two variables. Correlation is typically represented by an R value, which Hari briefly touched on. It's unitless. There are a few ways to tell if data is strongly correlated or weakly correlated. And just as a note, correlation does not imply causation at all. Just because 100% of people who drink water die, it doesn't mean that it doesn't mean that water is a direct cause of death, as you could infer. What is an R value? An R value is any number between -1 and 1. If the R value is negative, then so is the slope of the LSRL, and if the R value is positive, so will the slope of the LSRL. And what this means is that if an R value is negative, or if the slope is negative, the general trend of the data is decreasing, and vice versa for positive. If they're positive, then the data is generally increasing. The closer the absolute value of R is to 1, then the more strongly correlated the data is, and the closer it is to 0, the weaker it is. an R value of 1 is extraordinarily rare in distributions, but what it basically implies is that every single point in the data forms a perfect line. Every data set, every data point is located on the regression line. The image that is shown on your screen right now is it gives you a general idea of a data set and different R values that could be correspondent to them. So you see in this upper left one, the correlation is it's hard to see, but the correlation is 0, and as you can see, there's not a general trend in this scatter plot. There's no way you can draw an accurate regression line that represents this data. And as you go farther and farther, you can see that there forms as the R value increases, the data set becomes more correlated. So for example, you can see a general downwards trend over here. You can see, and in this next one, you can see the general upward trend over here, so forth and so on. And once you get to this bottom right image, you can see that this is pretty strongly correlated. You can pretty accurately guess a regression line. So how would one calculate an R value? There is a formula that's about to be shown on your screen, and this is how you calculate R. You don't have to memorize this equation. You'll be given a formula sheet on your AP exam and on your tests to aid you in this. The X and Y, so the X and Y with the lines over them, these two, they're read as the X bar and the Y bar, and are the mean. S sub X and S sub Y are the standard deviations of X and Y respectively, and N over here is the number of terms in the data set. All right, now we're going to look at linear regression models, which is your introduction to LSRL. So regression analysis is a process to predict or estimate the relationship between the independent or dependent variables. So in this unit 2, we're only going to talk about linear regressions. Later on, we'll get into more complex types of regressions, such as the quadratic regression or exponential regression, but we don't need to focus on that right now. So linear regressions follow the standard linear equation, which is y equals ax plus b. In statistics, you're not going to be using m and b. Instead, you're going to use a and b for b being the slope and a being the y-intercept. Now, this equation isn't completely correct right now because you're going to want to have a hat over the y. So what this hat represents is it represents estimation. So as opposed to the actual y value. So for example, you have this equation. This will represent the regression, which is a general guess of what the values should be. And if you look at this lower equation, it represents the actual values. So you're going to want to be using a hat for any type of estimations you make to not get them confused. So there are an infinite number of regressive predictions given a distribution in scatterplot. The least square regression line, which is the LSRL, you've heard us talking about that in previous sections. This regression line is the best fit for a scatterplot. So while there are an infinite number of these, this is the very best fit. And we're going to be getting into this in 2.7 and so on. Now, let's talk about extrapolation. Extrapolation is finding values outside of the given scope of a distribution. So, for example, you could have a data set from 19 to 24-year-olds. Extrapolation would be finding what the data could be for maybe a 40-year-old. To utilize extrapolation, you have to use linear regression. And do note that the farther out you go from the domain of the distribution, the less accurate predictions will be. And real quick, let's look at an example of this. A regression line is developed using data from 19 to 24-year-olds on how comfortable they are with using technology from a scale of 1 to 10. And as you can see, it gives you the regression line equation. Note the hat over the y. And what it's asking us to do is predict the comfort level of a 45-year-old, and does the answer you get make sense? Age would be the independent variable in this example, and the comfort level it will be the dependent variable. So since we know the independent variable, the age of the person, 45, then we have all we need to find the comfort level of this said 45-year-old. Let's just substitute 45 into this equation, which would be 0.32, excuse my handwriting, times 45 plus 0.67. And what that's going to get you is 15.07. Now, that answers the first part, predict the comfort level of a 45-year-old. But does this make sense? Does this answer make sense? Well, no, it does not make sense. The technology comfort level is on a scale of 1 to 10, and we're getting 15. That's outside of the range. So let's look at why. So recall that when using extrapolation outside of the given domain, the predictions are going to be less accurate. 45 is way out of the range from domain from 19 to 24, which is why we got such a wacky number for our comfort level. So essentially, this you should be careful when using extrapolation, because you could be getting an answer that doesn't make sense. Alright, so let's look at residuals now. A residual is the difference between a point on the distribution. So it's a difference between a given point, a given value in the distribution, and the value predicted by a linear regression model. So let's look at a quick graph here. We have this graph. Now you can see that we're given a best fit line, and we're given 5 different points. So points closer to the regression line has a smaller residual, and points farther away from the regression line will have a larger residual. So you can see here the pink dot and the green dot, they're only 1 unit away from the regression line, which means their residual would be 1, and that means that they're more accurate. And as you can see here, this blue dot, it's 1, 2, 3, 4 units away from the regression line, which means it's going to be less accurately represented. Now, positive residuals values, keep in mind, residual values can be positive or negative. What a positive residual value means is regression line underestimates the actual value, since the actual value is greater than the predicted value. So take a look at the blue dot, green dot, and pink dot. They're all positive values above the regression line. This is positive 4 values, and this is the blue dot is positive 4 values above the regression line. The green and pink are positive 1 above. And the same thing goes for negative. So negative residual values are overestimated by the regression line. So look at this this orange dot over here. This is 2 units below the regression line. The formula to find residuals, it's pretty straightforward. Most of the time, if you're given a graph, you probably won't need it, but the residual is the actual value minus the predicted value. So the actual value over here, for the blue dot, the actual value is 8, and minus the predicted value, which will be 4, so which means it has a residual of positive 4. Another thing you can do with residual values, is you can plot the residual values and make a residual plot. Residual plots can tell you a couple things. They can tell you if a linear regression line is good for a data set or bad for one. So let's look at a couple examples of a residual plot compared to its actual plot. So as you can see here, we have 2 plots. This the left plot represents a scatter plot of a given distribution, and the right graph represents the residual plot of the left plot. So what can you infer from this? You have a distribution here. It looks like it's a pretty good fit for the distribution. It's a downward trend and it matches pretty well. And the residual plot is pretty scattered. This is one way you're going to be able to tell if the plot is good or bad. Good residuals should be randomly scattered with no evident pattern. So as you can see here, there's not really a pattern you can infer from this data set. Let's look at this next example here. We have 2 graphs. Once again, the left plot is representing a scatter plot with a distribution, and the right graph represents the residual graph. As you can see here, the residual here, it has a pretty distinct curved pattern to it. You can pretty easily draw a line, and it makes a pattern. What this means is it's a bad residual, which means that a linear regression line probably isn't the best choice for the data set. Now let's see if that's true or not. We can see here that the data set is also pretty curved. So it means that probably you're gonna want maybe a different kind of regression line to represent the data, and not a linear line like this. And now let's talk about the LSRS. The LSRL, sorry. What LSRL stands for is the least squares regression line. I mentioned this in 2.6, I think. So the LSRL is the best fit linear regression that exists for a distribution. And it's called this because the sum of all the squares of the residuals is the smallest possible value for that distribution. So as previously mentioned, we have an infinite number of possible regression lines, right? Each one of those will have different residual values, and they're gonna each be better or worse fits for the distribution. Now, you're taking the sums of the squares of each of the values, and for the least squares regression, that value is going to be the smallest possible for this distribution. The Residuals are squared to eliminate possible negative or positive values, because you're only looking at the impact of residuals, not the actual values of them. Like, you're looking at how far above or below, how much of an effect it has on it. And this value is called the coefficient of determination, or it's called r squared. The r squared value always lies between 0 and 1. If r squared is closer to 0, it means that the LSRL doesn't model the data at all. It's completely scattered. If it's closer to 1, it means that the LSRL models the data pretty well. For example, r squared value of 1 means that every single point given lies upon the line. Now, here's the formula to find the coefficient of determination, or r squared. So, as previously mentioned, LSRL lines follow the standard formula of a line. The y with a hat is equal to a plus bx. A representing the y-intercept and b representing the slope. Now, let's look at how you would interpret the slope statistically. To do this, there are 3 things that you need to consider: context, correct definition, and the word predicted. Context essentially means that you have to provide the units of the variables so that it provides context for whatever thing you're analyzing. Correct definitions is essentially if it's increasing, if it's decreasing, or are the numbers correct. You need to have the word predicted, because the LSRL is nothing more than a prediction of the distribution. It has nothing to do, it doesn't formally represent the actual data. So it's important to specify this for the AP test. How you would interpret the y-intercept statistically, it's the same deal here. You need to provide context, correct definitions, and the word predicted. Now let's look at how you would interpret the coefficient of determination. Now, it's not going to be completely the same as the slope or the y-intercept. You're still going to want context. You're still going to want correct definitions. But one thing different is you need to show the linear relationship. You need to show that the regression line is linear, because you don't want to get confused with other types of regression lines. Right now, it's not a big focus for us, but you need to, for the AP test, you need to know how to read a computer printout. So I'm gonna show you a sample printout over here. You're not expected to know all of these values right now. The unfocused values will be touched on later in Unit 9. But right now, what you do know is the y-intercept, the slope, and the standard deviation of the residuals. This isn't too important at this stage of the year, but later on, you're going to want to know how to read this. So just consider this as a early reminder. Let's look at 2.9 now. Analyzing departures from linearity. So first of all, what are influential points? Influential points, so there are 2 types of influential points: outliers and high leverage points, both of which you probably already know. Essentially what they are is that they are points of the data that could hold potential to significantly change the regression. It could highly change the regression and affect it. So this is an example of an outlier. For example, you have a value really far up higher than the rest of the data, which seems to be over here. And here's another example. Here's you have a point here, which is pretty far away from the rest of the data. That's just what an outlier is. An outlier is a point in which the y value is much higher or lower than the other values. High leverage points, on the other hand, are points where the x value is a lot higher than, or a lot farther away than the rest of the points. So for example, you have this here. This would be a high leverage point. As you can see, the x value is a lot farther away from the other values. Both of these you should keep in mind as influential points. Now we can look at transforming data in nonlinear regression. So sometimes, as we saw earlier in section 2.7, not all regressions or data sets are linear. For example, you have here, this is not linear. This would be an example of a nonlinear data set. So in this case, it's better to use an exponential regression model or a power regression model. To use either of these, you're going to need to know how to transform data. So firstly, let's look at how to transform exponential models. Exponential models are in the form of y equals a times b to the power of x. Now, don't forget the hat over your y to represent that it represents estimation. To transform and to linearize it is you're going to want to take the natural logarithm of both sides. So that's going to be the natural logarithm of y with the hat, of course, and set that equal to natural logarithm of a times b to the power of x. Now, since a and b to the power of x are multiplied to each other, you can separate those as an addition of natural logarithms, and since x is an exponent to b, that can be multiplied onto the outside of the natural logarithm, and this is going to be your transformed equation. So now you can see that the natural logarithm of y is in a linear relationship with x, and now you can find the LSRL. The y-intercept is going to be the natural logarithm of a, and the slope is going to be the natural logarithm of b. Now, let's look at how you transfer a power model. A power model is in the form of y equals a times x to the power of b. So slightly different from the exponential model. Instead of b to the power of x, it's x to the power of b. Don't forget your hat. Similar to the exponential model, you're going to want to take the natural logarithm of both sides, and the process is the same, so I'm just going to cut to what the equation should be. Once you take the natural logarithm of both sides, that's going to be the natural logarithm of y is equal to the natural logarithm of a plus b times the natural logarithm of x. As you can see now, the natural logarithm of y and the natural logarithm of x now have a linear relationship as well. And to find the LSRL, the natural logarithm of a is going to be your y-intercept, and your slope is going to be b. Now, how can you tell which one to use? So you're going to want to check your residual plots and the coefficient of determination, or r squared, and you're going to see if the residual plot represents a linear regression or a non-linear regression. And you're also going to want to check if r squared is close to 1 or farther away from 1. If the residual plot shows a linear regression, another regression model may work better, or there could be any influential points. Alright, so thank you everyone so much for watching. Make sure to like, subscribe, and share with all of your friends. If you need any clarifications, make sure to check out our notes on the Study Bubbly website, and also make sure to check out other people's videos and podcasts for other subjects, as well as our community's free notes from our websites. All links are in the description. See you guys next time.